Welcome to 13th lecture from chapter number 8. We are studying VLSI Design and we are continuing studying branching effort. In last lecture we introduced the concept of branching effort. Branching effort is available or is computed at points where the output of one gate, for example this, is driving two or more output gates. Right, branching effort is computed as the capacitance of input capacitance of the gate that is in the path plus input capacitance of the gate that is off path divided by the C path. Whereas the total branching effort or path branching effort is computed as the product of individual branching efforts. Here today in this lecture we will solve a numerical problem and we'll compute path effort capital F for this chain. Right, the path is highlighted as dotted blue line. Let's number these gates first. 1, 2, 3 and 4. We can see that gates 1, 2 and 3 are in the path, and there is only one place where we have branching effect, that is this, where the output of this gate number 1 is being divided between 2 and 4. So the branching effort at this node is computed as, according to this formula that we studied in last lecture, the input capacitance of the gate that is in the path. This is NAND 2, so C of NAND 2 plus C of the gate that is off path, this is C NAND 3 divided by the input capacitance of the gate that is in the path. So after we have done this, we know that C of NAND 2 is R plus 2. We have computed in our earlier lectures. Of NAND 3 is R plus 3. Oh, there is a plus in between, divided by R plus 2. So this can also be written as 2R plus 5 over R plus 2. This is small b. Since we have only one place where there is the branching effect, therefore the capital B, that is the product of all branching effects, is the same as B, because we have only one branch. That is, so capital B is the same as the small b, only in this case where we have only one branch. So this is capital B. In order to compute F, we know that capital F, path effort, is G times H times B, where G is the product of logical effort of all the gates in the path. Here we have gate number 1, 2 and 3 in the path. Therefore G1, G2 and G3, they will be multiplied together to compute this capital G. We know that G of gate number 1 of this node 2 is 2R plus 1 over R plus 1. G2 is of gate number 2, this is NAND 2, we know this is R plus 2 over R plus 1. All these expressions, we have proved all these expressions in our earlier lectures. And G3 is again node 2, which is 2R plus 1 over R plus 1. So this is how we compute G for this path. And computing H is straightforward. The output capacitance of the final gate divided by the input capacitance of the first gate, 10 C1 over C1. This is 10. So now we are ready to compute capital F, the path effort. Path effort would be G times H times P. We have computed G, we have computed H and B. So this is 2R plus 5 over R plus 1 times H, 2R plus 1 times G, G, should write G first. Okay, let's write G first. This is G, 2R plus 1 over R plus 1, R plus 2 over R plus 1, 2R plus 1 over R plus 1 times H, which is 10 times B, 2R plus 5 over R plus 2. So given the value of small r that we know this between 2 and 3, we can compute this f. And we have also studied in our previous lectures that we compute another quantity that we call as the path effort of a single gate. This is the average path effort that we compute indirectly from capital F. Here we have 3 gates in the chain, therefore small f in this case would be 1 over 3. There is a slight, as a part B of the question, there is a slight modification in the path. Now we have attached CL, which is 10 times C1 here instead of being here. So the path is now, as part B of the question, is this. Now the path is this. So how would you compute capital F and then small f for this new chain? Right. First of all, let's see how many branches are there. There is only one branch, the same branch, but the capacitance of the path is now different. The capacitance of the path is the capacitance of NAND 3. Capacitance of path is that of NAND 2. That is opposite of the case that we did in part A, divided by C of NAND 3 because NAND 3 is in the path. So C of NAND 3, we know this is R plus 3 plus C of NAND 2 is R plus 2 over R plus 3. So this is 2R plus 5 over R plus 3. Right. How can we compute G now? The capital G is now the small g's of all the gates in the path, G1 times G4. Now we have only 2 gates in the path, 1 and 4. So G of 1 is, it's a NOR gate, NOR 2 gate, 2R plus 1 over R plus 1 times G4. It's a NOR 3 gate, NAND 3 gate, R plus 3 over R plus 1. This is an expression. This is the expression for capital G. And capital H remains the same because this is the output capacitance of the last gate divided by input capacitance of the first gate. It remains equal to 10. So now we can compute F by multiplying G with H and with capital B. Since there's only one node, therefore capital B is the same as small b. So 2R plus 5 over R plus 3. And the last thing for this lecture is to compute average path effort computed indirectly using the path effort 1 over n. So now we have only 2 gates in the path, therefore this n would be 2. We'll continue studying gate delays from chapter 8 in our upcoming lectures. Thank you.